Hello everybody, thanks for joining us today. And today we are going to talk about the latest version of NOZZLE FEM software capabilities. NOZZLE FEM is a tool for FEM-based strength and stiffness calculations of nozzle or support junctions. During the webinar, we will cover such topics as who needs the specialized software for nozzle-to-shell junction, how NOZZLE FEM software can help you when designing vessels and pipelines, what types of elements and nozzles are supported, and new features of the latest software version. We will also show you a live demo of NOZZLE FEM software. And besides, we will highlight an integration of NOZZLE FEM with START-PROF software for pipe and stress analysis. Today we have two presenters, Andrei Krasnokutsky, the head of the Strength Analysis Department, and Dr. Alex Matveyev, the head of the START-PROF Development Group. Now, I would like to invite Andrei Krasnokutsky to start the webinar. Andrei, please start.
Hello, dear colleagues. Let's introduce myself. My name is Andrei Krasnokutsky. I am the head of the PostProcessor Software Development Group. PostProcessor software consists of two programs, PostVessel and PostNozzle FEM. All calculation methods can be divided into two types, the so-called design by rules, early design by formulas, and design by analysis. Design by rules, this is the calculation of the vessel safeties such as strength, stability, buckling, tightness, and other using formulas. The formulas are in the codes such as ASME 8, Division 1, Division 2, EN 13445-3, and other. And the calculation is carried out for certain standard elements, shells, heads, nozzle, flanges, supports. If the construction is not described in any standards, or the application conditions are not met, you must use design by analysis. Design by analysis is a stress calculation using numerical methods, mainly the finite element method. This method allows you to calculate almost any construction with any loads. PostProcessor is a program that calculates the safety of vessel using for formulas or design by rules. In this program, the internal beam finite element model is used only to determine the loads in all elements, but not to calculate the strengths. We plan to talk about PostVessel program in a special webinar on December 4. The PostNozzle FEM is designed for stress and flexibility calculation mainly of nozzle-to-shell junctions, using the finite element method, so-called design by analysis. In this webinar, I present your attention to PostNozzle FEM program, which uses fair calculation. Why do you need NOZZLE FEM program? The problems of calculation the strength and stiffness of nozzle time nodes are often found in the design of vessel or pipeline. It's usually necessary to determine the allowable loads on the nozzle or perform calculation at specified loads. In the slide, you can see typical drawing of column with maximum allowable nozzle load table. There are several methods to solve this problem. First, using the analytical method, as per industry standards such as YRC 537, firmly 107, 297, EN standard, PD, codes, and others. Or you can use a numerical method, mainly by the finite element analysis programs. All programs that use the finite element method can be divided into two classes, universal and specialized. You can use universal software such as ANSYS, Natran, Cosmos, Abacus, and so on. Or you can use specialized programs such as PostNozzle FEM or NOZZLE programs. Analytical approach. The main advantage of analytical approach is the simplest and fastest solution. But it has a number of significant advantages, such as the scope of application mainly is limited by cylindrical shell and convex heads. Only radial and so-called single nozzles are considered. Oblique nozzles are not available. Single means that the distance between adjacent nozzles should not be less than the root of diameter multiplied by the thickness. Analytical approach gives us conservative results. According YRC, EN, PD calculations are carried out only for shells, bottoms, and the strength of the nozzle themselves from local stresses is not checked. Only YRC 297 has such a check. And temperature stresses are not taken into account when using shell and nozzle materials with different coefficient of thermal expansion and or different temperatures. Universal FEM software. Oh, it's great. It has practically no restrictions on the design and types of tasks to be solved. Universal programs can calculate any structures, not only for strength and stability and static setting, but also for dynamics, natural frequencies and shapes, temperatures, gas dynamics, and others. These programs such as I said before, ANSYS, Nastran, Cosmos, Abacus. But application of this program has several disadvantages. First, you will have to do a lot of work yourself. Creation of design models, including geometry, choose materials, apply loadings, and fixation conditions. After that, you need selecting the type of elements and creating a finite element models. Carrying out the calculation with choose of solution method. But the most important thing, you must mainly differentiate the received stress and evaluate them. Using FEM software requires skills in different disciplines. Surface and solid modeling, strength of materials, numerical methods, and at last, universal FEM software is very expensive. In this slide, you can see figure 5.1 for MASME A division 2 with stress categories and limits of equivalent stress. Next, let's look at the main features and advantages of NOZZLE FEM program. NOZZLE FEM supports a wide variety of shell nozzle configuration. The program doesn't require special knowledge or skills. The creation of a finite element model, the differentiation according to the received stresses, and the assessment are obtained automatically. It requires minimum time spent to obtaining results. And an advanced postprocessor allows us detailed consideration of the results. The possibility of connecting not only several nozzles, but also building structures and supports, including skirt. Calculation of not only the strength, but also the stiffness of connection, which is important to refine the loads from pipelines. In addition to external loads, hydrostatic and temperature loads are taken in account if necessary. The program can perform fatigue analysis. If the application conditions are met, additionally perform the calculation according to YRC and automatically generating HTML and FTF report. First of all, you need select and design configuration, attachment types and their number. After that, select a order of stress analysis, select additional finite element calculations, allowable loads, stiffness, sieves, and some analytical methods, like YRC, and set parameters to control calculation accuracy. Attachment elements. Program allows the next configuration. Shell without attachments. For example, if you need to calculate a conical reducer or conical head with a central nozzle. Next, several nozzles and all several structures. We can add up to 5 items simultaneously. Band support. It may be important for pipeline designers, since there is no analytical solution to the strength of such a structure. And skirt support. In this case, it is important to clarify the calculation if the diameter of the skirt is less than the diameter of the shell. And all the skirt and bottom are made of different materials with different coefficient of thermal expansion. All this leads to additional stresses that cannot be calculated analytically. Supported codes. You see different codes for estimation stresses. ASME, EN, GB, GHOST, PNI. It should be noted that the received stresses don't depend on the codes. Only estimation is carried out according to the norms. For example, ASME A division 1 differ from ASME division 2 by values of allowable stresses, or in the method of determining the equivalent stresses. For example, the zero or maximum tangential stresses, so-called TRISCA, or the maximum distortion energy, yield criterion from Mises. Last criterion used in ASME codes. Accuracy of results. The accuracy of results depends on the size of finite elements. The larger the size, or the coarser grid, the lower values obtained at the intersection point. The program offers 5 levels of measure with different element size, from first order to 5th fine element. Additional safety stress factor have been introduced to account for the effect of element size on the resulting stress. The factor was taken into account when determining the allowable stresses. Stress factor for first level is 1.3 and for 5 levels equal 1.05. The program implements the so-called hot spot stress method with extrapolation stresses, which allows to get more accurate results with raw measure and reduce the additional safety factor. Nozzle element. Nozzle element may be used with different cross-section shape, not only cylindrical but also elliptical, flat oval, so-called tabloid, and have comprehensive nozzle junction set with reinforcing pads, with nozzle insert, with barrel, Trunnion connection, storage tank nozzle, including nozzle with so-called stone-shaped reinforcing plate, and with a welded toroidal insertion. Structure element setting is the same to the nozzle setting, except structure is always Trunnion junction. Can set not only round but rectangle reinforcing plate, and additional orientation properties, for example, cross-section rotation angle, and with different cross-section shapes, such as square and rectangle tube, plate, beams with different shapes, I, H, U, C, T, angle, and other. So, next, bend support. Bend support setting is the same to the structure setting, with additional orientation of the support related to the outlet. Skirt support. Skirt support may be cylindrical, conical, and cylindrical with conical forms, connected to elliptical, spherical, or paraspherical head. Attachment placement. The program has a comprehensive orientation set. Nozzle all structure elements may be radial, hillside offset, tilted, coordinate placement may be polar or Cartesian, and offset for legs axis for bend station, and tilted in section plate, and vector. Loads. The program allows you to calculate several loading cases on one model. For example, in operating conditions, under test condition, cyclic strength, fatigue, and so on. Loads can be applied in different coordinate systems, both at the edge of the nozzle and at the intersection point. Loads are automatically converted when switching between different coordinate systems. If necessary, hydrostatic pressure and thermal strains can be taken into account. Thermal strains. Program considers thermal strain expansion deformation, all structure elements materials that caused additional stress by constrained deformations. The reason may be different linear expansion materials or temperatures. In the slide, you can see example without and with thermal strains. And thermal strains increase common stresses to 37%. Load setting. The program provides two ways to set loads on nozzle the nozzle edge and in junction. In the edge, a typical case when the nozzle and supply pipelines are connected by flange. In this case, the design scheme, including the supply pipelines, ends on the flange connection, and the design loads on the nozzle are obtained at this point. Junction, a case when the supply pipelines ends at the place of junction into the shell. In this case, the design scheme, including the supply pipelines, usually ends on the outer surface of the shell, and the design loads on the nozzle are obtained at this point. Calculation in junction corresponds to the flexible connection between the pipeline and the shell, and has been obtained on the basis of from numerous field tests. When calculating the strength, the program automatically converts the load specified by the user at the junction point into equivalent loads on the edge with minimum nozzle length. Calculation stage. After creating the model and the load application, the program checks input data, creates geometric and finite element models, performs the calculation, and output results stress analysis. Report. Program creates comprehensive report which contains input data, strength analysis, additional tables, and can be generated RTF format. It's possible to use 3D postprocessor from the report and the toolbar menu with different capabilities. Change view, make screenshot, choose different paint modes, change load case, change color set, and other. Global loads. If necessary, NOZZLE FEM create two tables. First table for individual allowable loads without impact of other loads including pressure, and after that create second table for allowable loads that take into account the combined action. The values of the second table, as a rule, are conservative in nature. Therefore, it's recommended to display the values in drawing with rounding up by 20–30%. Stiffness flexibilities. Tables with stiffness flexibilities can be used to clarify the loads from pipelines. Because taking into account the rigidity of the inserts allows you to reduce loads caused by different thermal expansion. It's so-called the secondary loads. Integration capabilities. NOZZLE FEM has integration with the programs for calculating vessels, FEM, and pipelines, START-PROF. Main advantages of NOZZLE FEM program. It's a user-friendly modern interface, a wide range of shell types, nozzle and structure element junction types, and placement capabilities. Different nozzle cross-section shapes, and it's important, affordable price. Additional advantage our program is advanced preprocessor, which used before the calculation for viewing the model and loads. In the next slides, you see some examples. For example, connection between skirt and vessel including thermal stresses, nozzle in a rectangle, plate, with ability to see the hydrostatic pressure, conical reducer with two nozzles, and several nozzles and structures attached to the base element. In conclusion, let us once again highlight the main improvements in the latest version of the past NOZZLE FEM program. They are shown in this slide. There are multiple nozzles and structure attachments on shell head or bend, plate and two plates of the structure attachment, review the model with loads and boundary conditions, stress analysis according to latest version, ASME and EN codes, and internet licenses. It's our newest licensing system. And this slide shows some users of our program. Now, let's look directly at the calculation of nozzles in the program. In the example, consider an elliptical head on three supports with two nozzles. First of all, we choose three supports, yes, and two nozzles. Support strength analysis code, in this case, ASME 8 division 2. Choose a second mesh quality. We recommend choose second 03 and input extrapolation of local stresses. We don't input additional calculation by YRC because it's not possible. It's impossible such calculation. After that, we go to base element, choose elliptical head, vertical placement. Z-axis is vertical. Yes, it's no horizontal. It's our bottom head. And invert shell direction. It's important if we needed add calculation with hydrostatic pressure. After that, we choose the material of base element. In this case, it's from comprehensive database from elements SA 516 with 60 grade. Okay, and we can look on properties versus temperature. For example, allowable stresses. Okay, input geometry such as inner diameter, wall thickness, total allowance. It's equal corrosion allowance plus minus tolerance. Height of head, height of flange, height of cylindrical shell connected with our head, thickness center of head, tolerance, and allowance of our shell. And go to structures and nozzles. Structures, it's section I-beam without enforcing, geometry, material, and displacement of our structure. We can input in polar or Cartesian, yes, and rotate, degrees increase our picture, and input axial offset, in our case 700 millimeters, axis orientation from center for first support 0, for second support the same structure, different axis rotation 120 grades, third support axis 240 grades, and nozzles. The first central nozzles, cylindrical shape without additional reinforcement. Geometry, materials, and displacement. As I said before, it's central nozzle. Second nozzle is tilted nozzle, axis offset 400 millimeters, axial rotational, yes, and axis direction. Click here, you can see what's mean. After that, you input geometry materials and click on preprocessor. Preprocessor, we can see 3 support, central, and tilted nozzles. Nozzle A, nozzle B. If okay, we go to loads. For choose condition, operation, or fatigue, or testing condition, choose additional, maybe enable checking primary, local, primary bending plus secondary for design conditions, or all, if you not click here, only for operating conditions. Pressure, yes, adds hydrostatic pressure if need, in our case for height filling 4 meters with density of water 1000 kilogram per meter cube. Temperature, design condition, operating conditions, and external loads. All supports 1, 2, 3, nozzle A, nozzle B. Loads and supports we can receive from PASECUBE programs. And after that we click on calculator and program create finite element models. In this case, number of elements. Stiffness matrix before and after optimization. Optimization, calculate displacement and stresses of our models, and we receive report. Click on stress analysis by FEM and design on operating conditions. Click here. And we can choose mesh level, safety factor on mesh level, and allowable stresses for each element. After that, we can see finite element model. Yes. Equivalent membrane stresses from pressure. It's without concentration, without concentrator. After that, we see equivalent membrane stresses from action of forces and pressure. And sum of primary membrane plus bending principal stresses, yes, and membrane plus bending stresses on outside and inside surface. Click on any results. We go to postprocessor, where we have comprehensive instrument for detailed stress conditions, not only stress conditions. We can see that maximum stress in this case in bottom shell near support. Click with grid elements, without grid elements, deformation, yes. And not only this equivalent stress, we can see here any other false results. For example, displacement. Displacement, we can see displacement maximum in central nozzle in this direction from moments mainly. Yes, it's okay. And in end of our report, we can see minimum calculated safety factor is equal more than 1. It's mean that our stress condition is okay, fulfilled. Yes, thank you for your attention.
Thank you, Andrei, for your very useful presentation. And now I would like to invite Dr. Alex Matveyev to tell us more details about the integration of NOZZLE FEM software with START-PROF for piping stress analysis. Alex, welcome. You may start.
Okay, thank you. Do you hear me?
Yes, we can hear you well.
Okay, so let's proceed. Now I will tell you about the integration between the pipe stress analysis software and PAS-NOZZLE FEM software. It is the PAS-START-PROF and PAS-NOZZLE FEM seamless integration. Here is the user interface of the PAS-NOZZLE FEM, and this is the user interface of PAS-START-PROF software. So we have the complete integration. You can work in pipe stress analysis software and just, for example, click on the band or T element and to calculate the stress intensification factors, flexibility factors automatically. What this integration can do. The first is the stress intensification factor calculation and flexibility factor calculation for the T's, bands, trunnions on the band, trunnions on the pipe. So for non-standard elements, including the lateral T's, for example. And the second is the vessel nozzle and tank nozzle stiffness calculation and allowable loads calculation. And also it can analyze stresses in the nozzle. And the interesting feature is that PAS-NOZZLE FEM software is free for PAS-START-PROF users. So if you buy PAS-START-PROF license for pipe stress analysis, you will get the PAS-NOZZLE FEM for free. It will use the same dongle as PAS-START-PROF software. Let me remind you what is the stress intensification factor. The stress intensification factor is the ratio between the allowable stresses of a straight pipe with a butt weld and the component allowable stress. For example, band, or it also can be the T element, reducer, trunnion, and any other element. So the stress intensification factor is the ratio between that allowable stresses. How can they obtain the stress intensification and flexibility factors? Firstly, we can obtain them from the ASME B31 codes. Also, usually they have reference to the ASME B31J code. Also, you can find it in EN codes. But they have several limitations. We will talk about them later. Also, you can use some experimental data, some tests, and you can use the finite element method to calculate the stress intensification and flexibility factors, for example, using software like PostNozzle FEM. What about limitations in the codes, the code equations? The first limitation is that ratio between diameter, outer diameter, and the wall thickness of the pipes and T elements should not be greater than 100. The second limitation is that the T branch should be normal to the within 5 degrees to the surface of the round pipe. So you can't analyze the lateral T's, only straight T's. And also, it is not applicable for trunnions. And some other limitations that you can see here. This is the screenshot from the ASME B31J. How can they calculate the stress intensification factors using the finite element software? To do this, we need to create two models. The first model is the finite element model using, for example, shell elements. And we can calculate the maximum peak stress from this model. And we also should create the second model, it's beam model. And we also can calculate the maximum stress from the beam model. And after that, we should calculate the ratio between shell stresses and beam stresses. Also, we should divide it by 2 and multiply by the fatigue strength reduction factor, which consider the peak stresses in the shell model. And after that, you will receive the stress intensification factor. This is how the PostNozzle FM software calculate the stress intensification factors using finite element method with shell models. This is how the output report looks like. For example, here you see the stress intensification factors for T element, for header, and for branch. We have several stress intensification factor for axial force, in plane moment, out plane moment, torsion moment, and for pressure. Here you see the fatigue strength reduction factor, the maximum stress from the shell model, from finite element method, and nominal stress from the beam model. And after that, you can calculate the stress concentration factor, and finally calculate the stress intensification factor. If you use NOZZLE FEM through the START-PROF software, you can open the properties of the band T or some other elements, click the SIF button, and you will see the stress intensification factors. If you click calculate button, the PostNozzle FEM window will be automatically opened, and it will recalculate the stress intensification factors. Let me show you it's live. For example, we have following model. It's a piping system with some steel structures, and we have two pressure vessels here. This is the first pressure vessel, this is the second pressure vessel, and we have a nozzle object here and nozzle object here. And we have several bands, several T's. Also, we have some pump objects, and also we have a trunnion. This is trunnion on the pipe and trunnion on the band. So let me show you how to calculate the stress intensification factors. For example, I open the properties of this band, just double click on it. And here you see the SIF button. If you click here, you will see the stress intensification factors that will be used in the calculation, in the pipe stress analysis. And you can refresh them clicking this button, calculate. If you click it, automatically nozzle FEM opens and recalculate that factors. Okay, so the same way you can do with T element. For example, click here. This is the stress intensification and flexibility factors for the header of the T and for branch of the T. And also you can recalculate them using the finite element method. This is the matrix before optimization and after optimization. And it's quite quickly recalculate you the stress intensification and flexibility factors. Okay, so next thing is the lateral T's, for example. To analyze the lateral T, you just need to draw the branch pipe with some angle to the header pipe and insert the T. And after that, you can calculate the stress intensification factors, and nozzle FEM will create the following model for this T element automatically and calculate the stress intensification factor. And the interesting thing is that many companies use the simple approach. They calculate stress intensification factors for the straight T's and just multiply them. Some companies multiply by 2.0, some companies multiply by 1.7, and receive the stress intensification factor for lateral T with 45 degrees. So we tried to check this method, and we find that it is incorrect because actually the stress intensification factors for the lateral T is lower than the stress intensification factors for the straight T. You see, this is the 5.0, and here you see 3.2. So it's lower than for straight T, and the same with all other stress intensification factors except the torsional moment stress intensification factor. It is the only factor which is greater for the lateral T. So this approach is too conservative. And also, pass nozzle FEM can calculate the Trunnion elements, which is not described in any codes. You can't find the stress intensification factors for them, but using nozzle FEM software, it's quite easy. How to do this? For example, here it is the Trunnion element. This is the Trunnion element. You can insert it like just ordinary T. It's here, this band with Trunnion. You open its properties, also click SIF button and just click calculate. So pass nozzle FEM will automatically calculate stress intensification factors for the Trunnion element. Okay, it's almost finished. Okay, so it was not changed because I already calculated them. So let me show you the model. START-PROF automatically create the following model for the Trunnion element. You can't see this model because it's hidden, it's in second layer, but START-PROF automatically create this model. This is the rigid element, this is the Trunnion, and it put the stress intensification factor and springs with specific flexibilities using that K factors in this point. And also it apply the stress intensification factors and K factors for this band element. So it's automatically modify the model. And the same way you can calculate the Trunnion on the pipe element. So it's like ordinary T, reinforced or unreinforced fabricated T, but without opening between header and branch. And automatically for any T elements, including this element Trunnion on the pipe, START-PROF automatically create the advanced model. It's also the second layer model. It's hidden. You can't see this model. But in fact, START-PROF put the rigid element here on the branch and put flexibilities in this point on the branch and in 2 points on the header. And consider the flexibilities calculated using the finite element method. If you have a lot of objects, for example, you have a lot of bands, a lot of tees, you can calculate them all. For example, when you run analysis of your model, like this, START-PROF show you the question, do you want to recalculate all objects? I will just demonstrate you, but I will cancel this calculation. So you click OK. The Pass Nozzle FEM window opens, and you can see all the elements in this model which are recalculated using the finite element method. Several nozzles, several trunnions, elbows, welding teeth, and so on. Okay, so I just cancel calculation because it will take some time. I want to save the time. And after finite element calculation, the ordinary pipe stress calculation proceed. Okay, so this is how it works. And the next feature is the nozzle flexibility calculation and stresses in the nozzle calculation, and also allowable loads calculation. So how can they calculate the nozzle flexibilities and stresses? The first method is using the analytical methods. It's WRC code 297 or 537. I think all of you already know it. The next is PD 5500, and the third method is using the finite element method, using the software like Pass Nozzle FEM. The WRC 297 and 537 codes have a lot of limitations. You can see them here. It's some ratios between diameters, wall thicknesses, and also there are limitations. For example, that codes can't be applied for can be applied only for non-protruding nozzles, for nozzles without reinforcement, and only for cylindrical and spherical shells. So it is not applicable for tangential nozzle at not normal angle to the vessel surface, nozzle protruding inside the vessels, trunnions with reinforcement for conical shells, flathead, rectangular plate. So there are a lot of limitations. But with Pass Nozzle FEM software, you can overcome all the limitations. You can use the nozzles, for example, tangential nozzles, protruding nozzles with reinforcement, with different type of reinforcements, and it can be connected to the rectangular plates, flat heads, conical shells, and so on. So in with any other base elements. So how to use it in START-PROF software? In START-PROF we have a special object, it's called vessel nozzle. In this object you can choose to analyze nozzle flexibilities using finite element method and allowable loads or stresses. Also you can use the finite element method, and it can be automatically calculated using finite element method. Let me demonstrate this. For example, we have a nozzle here. This is the pressure vessel, and we have a nozzle object here. I just double click this vessel nozzle, and for example, for nozzle flexibility, you can use rigid, no flexibilities, manually input flexibilities, use WRC code, use PD code, and use finite element method. And for allowable loads, you can choose not to check allowable loads, define manually allowable loads, use WRC code to calculate stresses in this nozzle, use finite element method to calculate stresses in this nozzle, and calculate allowable loads using finite element method. If you choose stress check using finite element method, START-PROF will run NOZZLE FEM model before analysis. For example, if you click here, run analysis, START-PROF will call NOZZLE FEM software, and it will calculate the flexibilities of that nozzle. After that, the pipe stress analysis will be performed, and after pipe stress analysis, START-PROF will transfer the loads on this nozzle element and run NOZZLE FEM software to calculate stresses in this nozzle. So if you choose stress check by FEM, the NOZZLE FEM software will be run twice. First time before analysis of pipe stress system, and the second time after analysis. This method is less conservative. And another method is to use the allowable loads calculation. In this case, START-PROF will run NOZZLE FEM analysis only once before pipe stress analysis to calculate allowable loads and calculate the flexibilities. But in this case, the results will be more conservative because allowable loads are several times lower when it can be if you will just use the stress check by finite element method. But it consumes less time and less resources of your machine. Okay, so how you can define the properties of the nozzle? You just click here on this button, and you will see the special user interface of NOZZLE FEM software, where you can define the properties of the base element. You can choose to which element your nozzle is connected. For example, it can be vertical vessel, horizontal vessel, storage tank. It can be conical shell, conical reducer, conical head, elliptical head, and many others, including, for example, flat heads. And also it can be the rectangular plate like this. And of course it can be bent, but it's mainly used for trunnions. And the next thing is the properties of the nozzle. You choose the nozzle type. You choose the reinforcement type. Is it set in, set on, with reinforcing pad, with internal part, and some others. Okay, so you just choose the type of reinforcement, the define geometry of the nozzle, define the angles, how it is connected to the base element, and after that you can just run analysis. I will cancel. Okay, so this is how it works. And if you have, for example, 100 nozzles in your model, START-PROF will automatically calculate 100 nozzles using NOZZLE FEM software. And also, as I said, the NOZZLE FEM software is free for START-PROF users. So, for example, if you have the START-PROF dongle, you just, and you have a license, you just go to service, run NOZZLE FEM, and NOZZLE FEM opened using the same license as START-PROF, and it's absolutely free for START-PROF users. So you can work with NOZZLE FEM software. And of course, you can use the results of NOZZLE FEM software when you perform analysis, for example, in Caesar tool software. But in this case, you will have to transfer data manually. So you just need to copy to clipboard the values of the stress intensification factor and paste it in Caesar tool. But with START-PROF, we have seamless integration. You don't need to do this manually. Okay, so I'm finished, and I give the word to Marina, please.
Thank you, Alex. I hope that attendees of our webinar have got some new information today. Please contact us by email or by WhatsApp. You can see the QR code on the screen right now. And so thank you, everybody. Thank you, Alex and Andrei, for this wonderful presentation. Have a good day.